Today we're starting a new unit on radical functions, and the first lesson is on rational exponents. Before we start this lesson, everyone should take a moment and go over the exponent properties worksheet, the exponent properties note sheet. That will definitely be helpful when you are going through the different exponents on the notes today. So if you have a base of b and it's in exponential form, when you convert it to radical form, the base goes underneath the radical symbol. It's the whole number underneath the radical symbol. If you have an exponent in exponential form, the numerator of your exponent is going to be the exponent underneath your radical symbol. And if you have a denominator, so if it's a fraction with a denominator, then the denominator of the fraction will become the index of your radical. Now, this form here is identical to this form here. So whether you write the exponent on the inside or the exponent in parentheses on the outside of the rational form or radical form, then that's completely fine. If I gave you a basic example, just to kind of put numbers to this form here, if I gave you 2, actually let's do 4, raised to the power of, let's do 1 over 2, 4 raised to the power of 1/2. Based on this rule above, I can rewrite this knowing that my base is going to go underneath my symbol. So 4 is the base. I know that the numerator of my exponent is going to be the exponent underneath this square root symbol. And the denominator of the exponent is going to be my index. So I can rewrite 4 to the power of 1/2 as the square root of 4. Of course, you don't need that square root. You don't need the index of 2. And you also don't need this exponent of 1. So I could just write this as the square root of 4. So this and this are identical. They are equivalent. If we look at these examples, example 1 is x to the power of 1/6. Remember that the exponent numerator is going to become the exponent underneath the radical sign, and the denominator is going to become your index. So this is going to be the 6th root of x to the first power, or just the 6th root of x. This is your radical form. Number 2 has a negative sign, and before I go over that, we actually need to review negative exponents quick. We do see negative exponents quite a bit, so I'm going to write a note and then I'll go over that with you. Okay, so my note says that negative exponents become a positive exponent in the denominator. So check out this example here. I have a to the power of negative n, and all I did was rewrite this as 1 over a to the power of positive n. So it just moves to the denominator, becomes a positive exponent. This is important. We use it a lot in this lesson. So looking at this example, number 2, we have y raised to the power of negative 7 over 2. So right away, I notice I have a negative exponent, and we can't have that. So I'm going to rewrite this as 1 over y to the power of 7 over 2. So now I have a positive exponent, but it's in the denominator. So this here is going to be rewritten as 1 over the square root, because the denominator is 2, and that's the index, of y to the 7th power. I'm not quite done with this problem here. We need to actually simplify this. So we need to rationalize the denominator, or simplify it however you choose to go about this, whichever one you decide to do first. For this example, I'm going to rationalize it first. So because our index is 2, we want to make even groups of 2. Well, we have 7 values of y already, so I'm going to multiply the top and bottom by one more value of y. That's going to give me the square root of y divided by the square root of y to the 8th. So again, I just noticed I had 7, so if I multiply it by one more value, that gives me my value of 8. Oops, sorry. And now I can simplify. My numerator does not simplify. It's going to remain as the square root of y. However, the denominator has 4 even groups of 2, so I'm going to rewrite the denominator as y to the 4th. So whenever possible, rationalize, or if necessary, rationalize. All right, I'll quickly go through the on your own section. You can follow along. A couple of these require simplifying, and one of them requires rationalizing. So make sure you pay attention to those. In the next example set, we're working the opposite way. So we're given radical expressions, and we have to convert these to exponential form. So remember that the exponent underneath the symbol, the radical symbol, is going to be your numerator, and the index is your denominator. That means this one here is going to be z as the base, 1 is our numerator, 4 is the denominator of the exponent, and that's it. That's your converted form. Number 2, recall that a problem like this, right back to the beginning, so top of the first page, this is exactly the same as saying the fifth root of y raised to the power of 4. So whether the index is inside or on the outside of your expression, you do have the same form or the same type of problem. So the base is y, the exponent on the inside is 4, the index is 5, 4 over 5 is your exponent. And just watch closely as I go over the on your own section. And next we're evaluating expressions. The expressions that you see here are both in exponential form, which you probably don't really know how to evaluate at this point. But what we just learned is converting into radical form. So that makes it a little bit easier. Not that it changes the problem, it just makes it easier to visualize, or obviously you're more used to, I should say, it's more normal for you to see a radical than an exponent like this. Anyways, the denominator of that exponent is 3, so that's our index. This means we have the cube root of 216 raised to the power of 1, which is just 216, and the cube root of 216 is 6. That's your answer. Do you have to convert it to this form? Not necessarily. You just have to understand what this is asking. For number 2, we have 84 raised to the power of negative 1/4. So I'm going to rewrite this as 1 over 81 raised to the power of positive 1/4, which becomes 1 over the fourth root of 81. And the fourth root of 81 is 3. That's 3 to the fourth power is equal to 81. That means we have 1 over 3 as our final answer. Again, don't necessarily have to write out all those steps. Just understand what 81 to the negative 1/4 power is asking. For the next two examples, we have a little bit more going on. As you can see, number 3 is 2 bases with exponents being multiplied. So when you have the same base, you can add the exponents. That goes right back to basic exponent rules. And when I say same base, we're talking about this number 7. And when you're adding fractions, sometimes you need to write out some extra work. I think everyone here probably knows that 1/2 plus 1/2 is just going to be a value of 1. So if we write this as 7 with an exponent of 1/2 plus 1/2, I hope you all know that that's just a value of 1. So this is just 7 to the first power, or 7. Definitely a good rule to remember that you can add the exponents when the base is the same. Okay, say you didn't get that rule. Say you just totally started this problem by using the method of converting to square roots. So if that was the case, we'd have 7 to the power of 1/2 times 7 to the power of 1/2. And hopefully you would, hopefully you would all change this to the square root of 7 raised to the power of 1, square root because the denominator is 2, so the index is 2, times the square root of 7. Then you would multiply those together to give you the square root of 49. Then you would say the square root of 49 is 7. So two different methods arriving at the same answer. However you feel comfortable doing it, just make sure you know the correct rule and how you can go about doing that. For number 4, we can't exactly do the same thing here because the bases are not the same. So if the base isn't the same, the only thing we can do is convert to radicals and see if we can simplify. 5 to the power of 1/4 is the 4th root of 5 times the 4th root of 125. Luckily, if you have the same index, then you can multiply radicals. This is what we went over last class. If you have the same index, you can multiply them together. This gives us the 4th root of 5 times 125, which is 625. And the 4th root of 625 is 5. Next, the directions just tell us to write the final answer in radical form. So we're simplifying this. You can approach it in any way you want to. However you do that, just make sure your final answer is in radical form because that's what the directions tell us. So number 1 is something that previously I've said that you cannot multiply together because we don't have enough knowledge to do that. And what I'm talking about is because we have the square root of 7 multiplied by the cube root of 7. I'm just going to write this out like this. Okay, so we can't multiply these together because we have different indexes. If we have different indexes, then radicals don't help us, but I do recognize that we will have the same base if we convert to exponential form. So that's the approach that I'm going to take. I'm going to change this to 7 raised to the power of 1/2 multiplied by 7 raised to the power of 1/3. Once you convert to exponential form, you can add the exponents. This would give us 7 raised to the power of 1/2 plus 1/3. Well, 1/2 plus 1/3 is two fractions that have different denominators. If I do this off to the side, 1/2 plus 1/3, a common denominator would be 6. Multiply the first fraction by 3, the second fraction by 2. We get 3 over 6 plus 2 over 6, which gives us 5 over 6. Coming back to the problem, 7 raised to the power of 5 over 6 is going to be your answer in exponential form, but remember the directions that I highlighted say to write your final answer in radical form. So I am going to write my final answer as the 6th root of 7 to the 5th. Now, if you have a calculator, which you might not, but if you do, then you could expand this out. 7 to the 5th is 16,807. But for a big number like that, obviously you would need a calculator. If you don't have one in front of you, I'll accept either answer. And for number 2, here's another issue that we have, so very similar to number 1. I'm actually just going to take this note and draw an arrow because, once again, we have 2 different indexes, therefore not very helpful. Can't simplify doing anything besides converting to exponential form. My numerator becomes x to the power of 3 over 4 divided by my denominator, which is x to the power of 2 over 8. When you are dividing with the same base, which we do have, that means you can subtract your exponents. This is an exponent rule. So this becomes x to the power of 3 over 4 minus 2 over 8. 2 over 8 can be simplified. So I have x to the power of 3 over 4 minus 1 over 4. This is x to the power of 1/2. That's in radical form. So if I was, it would actually be 2 over 4, but 2 over 4 simplifies to 1/2. Convert that to, I'm sorry, this is in exponential form. Convert that to radical form. We have the square root of x. And the last example set also doesn't matter how you go about this, but your final answer needs to be in exponential form. For number 1, we have the cube root of 64 times z to the 6th. Well, 64 is a perfect cube. It's 4 cubed, so I'm just going to leave that as 64. But z to the 6th I'm going to break down to 2 groups of 3. Now I'm going to rewrite this as 4 times z, which is 4 times z squared. And that's already exponential form, so we don't even have to do any more with that. That is our final answer. Number 2 is a big one. You're definitely going to see this on a quiz, just as a hint. But this is in parentheses 27 times x to the 6th times y to the 9th raised to the power of negative 1/3. We have a negative exponent. So negative exponents become positive in the denominator. That means I can rewrite this expression as 1 over, in parentheses, 27 times x to the 6th times y to the 9th raised to the power of 1/3. That would be positive 1/3. Now, I like to convert to radical form because I'm used to seeing it that way. But we can simplify, whether you simplify in exponential form or you know that you want to convert to radical form, which is what I'm going to do. Our denominator becomes the cube root of 27 times x to the 6th times y to the 9th. And at this point, as far as we've been simplifying, 27 is a perfect cube, x to the 6th is 2 groups of 3, y to the 9th is 3 groups of 3. So my final answer is 1 over 3, the cube root of 27 is 3, x squared, y cubed. And that is already in exponential form, so we're going to leave our answer alone. This is our final answer. I'd like to take a moment and go over a couple of extra examples. These extra examples use a couple more of the exponent properties from our chart over here. So looking at number 1, like I said, we're going to be using the product rule. And this tells us that if you have the same base, you can add your exponents. We have a base of x for each of these, which tells us we can add our exponent of 2/5 and 8/5. When I write this out, I have x to the power of 2 over 5 plus 8 over 5. Of course, when you do this, you make sure you simplify any exponent or any fraction that you can. This leads us to x to the power of 10 over 5. You add fractions, you add your numerators, your denominator remains the same. And then, of course, for your final answer, 10 over 5 is going to simplify to 2. X to the power of 2 would be your final answer. For number 2, we have x raised to the power of negative 3 over 4 raised to the power of negative 1 over 6. And this is going to be the power rule. So when we are using the power rule, that tells us that you can multiply your exponents. This is going to become x to the power of negative 3 over 4 times negative 1 over 6. When we multiply these exponents together, two negatives make a positive. This gives us 3 over 24. That's positive 3 over 24. We simplify that exponent to 1/8. X to the power of 1/8 is your final answer. And our last example, number 3, is going to use the power of a fraction rule. And this rule tells us that if you have the same base, you can subtract your exponents. And lastly, number 3. Number 3 uses the quotient rule. I think I actually highlighted the wrong one above. I did. Sorry, I mentioned quotient rule. I just highlighted the wrong one. So the quotient rule tells you that if you are dividing, that's the same thing as a fraction. If you are dividing something with the same base in both the numerator and the denominator, you can subtract your exponents. So in this example, we end up with x to the power of 3 over 4 minus 1 over 8. Those are the exponents we're dealing with. When you're subtracting fractions, you need to make sure that you have a common denominator. I can easily make 3 over 4 into a common denominator with 1 over 8 by multiplying 3 over 4 by 2. This becomes x to the power of 6 over 8 minus 1 over 8. Our final answer, when we subtract our numerators, gives us 5, and our denominator remains as 8. Of course, that is an exponent, so x raised to the power of 5 over 8 is our final answer. There are multiple ways to get to these answers. If by chance you want to convert to radicals, you can do that. I don't think that would be helpful in this case, but that is always an option. Please let me know if you have any questions.